We conclude our study of multiple integration by looking at integration in cylindrical and spherical coordinates. So integrating in cylindrical coordinates is a fairly natural extension from integration in polar coordinates. We start with the simplest bounded region, B in R3, in the form of a cylindrical box. That is, B is the set of all ordered triples R theta Z, such that A is less than R less than or equal to B, alpha is less than or equal to theta less than or equal to beta, and C is less than or equal to Z less than or equal to D. We divide each interval into L, M, and N subdivisions respectively, such that delta R is B minus A over L, delta theta is beta minus alpha over M, and delta Z is D minus C over N. So if we look at such a cylindrical box, and we let R ijk star, theta ijk star, Z ijk star be any sample point in the cylindrical subbox B sub ijk, then we can define the triple integral in cylindrical coordinates as the limit as this max goes to 0 of this triple sum. For a continuous function on the region given by theta 1 less than or equal to theta less than or equal to theta 2, R1 of theta less than or equal to R less than or equal to R2 of theta, and Z1 of R theta less than or equal to Z less than or equal to Z2 of R theta, the triple over this region W of f of x, y, z dv is a triple iterated integral. It's the integral from theta 1 to theta 2 of the integral from R1 of theta to R2 of theta of the integral Z1 of R theta Z2 of R theta of f of R cosine theta R sine theta Z R dz dr d theta. Again, note this R part here again. Just as with polar, we get an additional R. We convert dv into its polar, or in this case, I'm sorry, cylindrical form. So we will go ahead and find the volume of the region bounded below by the R theta plane, above by the sphere x squared plus y squared plus z squared is equal to 4, and on the sides by the cylinder x squared plus y squared is equal to 1. So since we have x squared plus y squared plus z squared is equal to 4, we can write this as r squared plus z squared is equal to 4. Right, so z squared would be 4 minus r squared. So from here we can conclude that negative square root of 4 minus r squared would be less than or equal to z, less than or equal to the square root of 4 minus r squared. Now we have x squared plus y squared is equal to 1. So r squared is equal to 1. And so from here we get 0 is less than or equal to r, which is less than or equal to 1. Right, and obviously we're also going to know that 0 is less than or equal to theta, which is less than or equal to 2 pi. Now there's only one more restriction we have. It's bounded below by the r theta plane. Since below is the r theta plane, z will actually always be positive. And so this here describes our region W. So we can set up now our volume. Remember, the volume of a region is just the triple integral over that region, dv. So we're going to have integral from 0 to 2 pi, integral 0 integral 0 to 1, integral 0 to the square root of 4 minus r squared, r dz dr d theta. And since we're not going to have anything ever in terms of theta, we can just completely integrate with that first, and we'll have 2 pi, then integral from 0 to 1, integral from 0 to the square root of 4 minus r squared of r dz dr. So we'll have 2 pi times the integral 0 to 1 rz. Z goes from 0 to the square root of 4 minus r squared dr. So this gives us 2 pi times the integral from 0 to 1 of r times the square root of 4 minus r squared. And this is simple u sub, so we get negative pi times 2/3 4 minus r squared to the 3 halves, evaluated from r equals 0 to 1. So we get negative 2 pi over 3 times 3 square root of 3 minus 8. And if we want to distribute that negative through, we can, and we'll have 2 pi over 3 times 8 minus 3 root 3. And we'll just leave it like that. So now we're going to add integration in spherical coordinates. So consider the small spherical wedge that is shown over here. So this is the wedge we're looking at right here. We see that the wedge is nearly a box with sides of delta rho, rho times delta phi, and r times delta theta. We have to compute or convert r delta theta into spherical coordinates. Now, since delta theta is already in spherical, this is broken down to just converting r into a spherical component. So remember that r squared is x squared plus y squared. So this is rho times cosine of theta times sine of phi all squared, plus rho times sine of theta times sine of phi all squared. So we're going to have a rho squared sine of phi squared. So rho squared sine squared of phi times cosine squared theta plus sine squared theta, which of course this piece is just 1. So we're left with rho squared sine squared of phi. So r is just rho sine of phi, and r delta theta would then be rho sine of phi delta theta. So the volume of this wedge would be delta v is equal to rho squared sine of phi times delta rho delta phi delta theta. Now, if the wedge is described as alpha less than equal to rho less than equal to beta, or A less than equal to rho less than equal to b, alpha less than equal to theta less than equal to beta, and gamma less than equal to phi less than equal to psi, we can then divide each interval into L, M, and N subintervals, such that delta rho is b minus a over L, delta theta is beta minus alpha over n, and delta phi is psi minus gamma all over n. Now, if we have such a region, and f is continuous on it, and rho ijk star, theta ijk star, and phi ijk star is any sample point in the spherical subbox b sub ijk, then we can define the triple integral in spherical coordinates as this limit here. Now for a real w, that's described as theta 1 less than equal to theta less than equal to theta 2, phi 1 less than equal to phi less than equal to phi 2, rho 1 of theta phi less than equal to rho less than equal to rho 2 of theta phi. The triple integral over to f of x, y, z dv is again the triple iterated integral. It's the iterated integral theta 1 to theta 2, integral phi 1 to phi 2, integral rho 1 of theta phi to 2 of theta phi, of f of rho cosine theta sine phi, rho sine theta sine phi, rho cosine phi, rho squared sine phi d rho d phi d theta. Just as with polar and cylindrical, there is an extra term that is attached. This time it is rho squared sine of phi. So now we will find the volume of the region W that is bounded below by the cone z equals the square root of x squared plus y squared, and above by the sphere z is equal to x squared plus y squared plus z squared. So z being equal to the square root of x squared plus y squared means that rho cosine of phi is equal to rho times sine of phi. So this means as long as rho is not 0, cosine of phi has to equal sine of phi, which means that phi itself would be pi over 4. Now, z equal to x squared plus y squared plus z squared means that rho cosine of phi is equal to rho squared. And so, from here, rho would be just cosine of phi. We have no restrictions on theta, so our region W can be described as 0 less than or equal to theta less than or equal to 2 pi, 0 less than or equal to phi less than or equal to pi over 4, and then 0 less than or equal to rho less than or equal to cosine of phi. So our volume would be the triple integral over the region W dv. So we would have integral from 0 to 2 pi, integral from 0 to pi over 4, integral from 0 to cosine phi of rho squared sine of phi d rho d phi d theta. And we're not going to have anything in terms of theta, so we can integrate out of 2 pi, be left with integral from 0 to pi over 4, integral from 0 to cosine of phi, rho squared sine phi d rho d phi. So 2 pi times the integral from 0 to pi over 4 of rho cubed over 3 times sine of phi, evaluated from rho equals 0 to cosine of phi, then d phi. So we have 2 pi times the integral from 0 to pi over 4 of cosine cubed phi all over 3 times sine of phi d phi. Now we can do this using simple u sub. So we're going to have a negative 2 pi over 3, right? We let u be cosine. It'll be cosine to the 4th phi all over 4. Evaluated phi equals 0 to pi over 4. So when you do all this out, we wind up a volume of pi over 8. The final two examples are not going to ask us to evaluate an integral. It's just going to ask us to convert the integral into cylindrical or spherical. So the integral we're going to convert to cylindrical is this integral right here. So if we go ahead and describe it in rectangular, right? Negative 1 is less than or equal to y, less than or equal to 1. And 0 is less than or equal to x, which is less than or equal to the square root of 1 minus y squared. Then we're also going to have x squared plus y squared is less than or equal to t, less than or equal to the square root of x squared plus y squared. Okay, now this piece right here, if we look just at these two, this is the right half of a unit circle, right? So this tells us that the radius of the unit circle is 1. We can also get that from here. Right? And this says that x always has to be positive, which is quadrants 1 and 4. So this is the right half of the unit circle. So right away, that'll give us negative pi over 2 less than or equal to theta less than or equal to pi over 2. So that tells us it's quadrants 4 and 1, and then r would be between 0 and 1. Now here, we just convert into polar, so x squared plus y squared r squared less than or equal to z less than or equal to just r. So if we go ahead and set up the integral, or rather convert it, so we have the integral from minus 1 to 1, integral from 0 to the square root of 1 minus y squared, integral from x squared plus y squared to the square root of x squared plus y squared of x, y, z, dz, dx, dy. This will be the integral from minus pi over 2 to pi over 2, integral from 0 to 1, integral from r squared to r of r squared cosine theta sine theta z, then r dz dr d theta, and just cleaning this up, we get integral from minus pi over 2 to pi over 2, integral from 0 to 1, and integral r squared to r of z r cubed cosine of theta sine of theta dz dr d theta. Alright, and finally, we will convert this integral into spherical. So again, if we just look at how w is described in rectangular, we have 0 is less than or equal to y, which is less than or equal to 3. Then we have 0 is less than or equal to x, which is less than or equal to the square root of 9 minus y squared. And we'll have the square root of x squared plus y squared less than or equal to z less than or equal to the square root of 18 minus x squared minus y squared. Alright, so this is a circle of radius 3. Now both y and x are positive, so that's quadrant 1. Right, so this is the top right corner of a circle of radius 3. Now we just have to try and figure this piece out. Alright, so if we go ahead and look at this piece right here gives us x squared plus y squared plus z squared is equal to 18, which is the sphere of radius root 18. However, x squared plus the square root of x squared plus y squared is equal to z, right? So x squared plus y squared would be z squared, so we have z squared plus z squared, which is 2z squared, equal to 18. Z squared is equal to 9, and so z would be equal to 3, which means that rho cosine of phi is equal to 3. but rho is the square root of 18. Right, and the square root of 18 is 3 root 2. So 3 root 2 cosine of phi is equal to 3, which means cosine of phi is equal to 1 over the square root of 2, which is 2 over root 2, and so phi is pi over 4. So what we wind up with, ultimately, is theta would have to be between 0 and pi over 2 because we're dealing with quadrant 1. We just saw that phi is between 0 and pi over 4, and rho would be between 0 and 3 square root of 2. So, integral from 0 to 3, integral from 0 to pi over 2, integral from the square root of x squared plus y squared to the square root of 18 minus x squared minus y squared of x squared plus y squared plus z squared dz dx dy can be written as the integral from 0 to pi over 2, integral from 0 to pi over 4, integral from 0 to 3 root 2 of rho squared, then times rho squared sine phi, d rho, d phi, d theta. And if we just clean that up, we get rho to the 4th sine phi, d rho, d phi, d theta. And with that, we conclude multiple integration. So we looked at double integration, we looked at triple integration, and then we looked at converting into polar, cylindrical, and spherical. Starting in the next video, we will begin to study the final branch of calculus known as vector analysis. And vector analysis will essentially bring everything that's been covered in Calc 1, Calc 2, and up to this point in Calc 3 into one final giant conclusion. So we're going to be bringing everything together